شكرا يا دكتور.
Okay, so let's start what we end up with. So yesterday we ended up with this going through all the optimization algorithms and how to reach or hit the global minimum of the loss function, even if you have a very complicated structure of the loss function. And we've discussed actually different optimization methods that might solve it and fit different problems. Well, so we ended up with this slide where we need to prepare the data for the deep learning models. So far, we've seen the constructions and how one can cook a deep learning model, not even a deep learning. Before that one, we know now how to compute or how to construct a machine learning model that can solve some of the problems, either regression problems or classification problems. And we also know how, from this lecture, we know how to cook deep learning neural network to solve much more complicated problems. So now the point is that are we able to use the data, like the raw data that we collected immediately or not? Like for example, I'm a data scientist, and my job actually is to analyze the some information about some users for some application, and then people just collecting the data like your age, your habits, your location, etc., etc. So the question now, are we able actually, or am I able to use this kind of information or data immediately, or I have to do some preparation or data pre-processing? So the answer is no, of course. We have to do what's called exploratory data analysis. And in this, we need to prepare the data before we use it in a machine learning model. So there are three things that we are going to discuss here. First one is this what's called data cleaning or data cleansing. Second one is how to handle the text and categorical attributes. Because we agree all together that dealing with a machine learning or deep learning models, then all our data has to be numbers, right? Because machine learning models do not understand anything except numbers. So sometimes the data collector are very lazy. Like we know all the Chinese, right? So Chinese are cheap. They do lots of very basic, inaccurate calculations, and most of the time they have wrong solutions, and sometimes they miss their job. Like for example, when you try to collect more data, then this data is not accurate, or sometimes you have lots of missing data, or even they are very lazy such that they keep the data in text. So how can we handle this? Also the feature scaling. So we are talking about this 3 data preparation steps in a moment. This kind of data that you might deal with. And as you can see, the data collector actually miss some of the information. Or maybe, like for example, if you are working on this Twitter or Facebook or other YouTube, for example, and then you have to do, at the end, you have to do some rating, right? So if you like the ad or something like that, but most of us actually are a bit lazy to hit the button and then you just do the rate. And actually, as you hit the rating button, actually, this is very, very expensive, and you give them a very good favor for the company, such that they analyze or have full picture about the data that they deliver. And sometimes maybe people actually are very lazy to rate the ads or rate the the application and things like that. And this is actually what's called here as a missing link. So in your data, actually, maybe you face something like that. And here, this is classes, first class, second class, third class. And here the name of some of the users, age, and some cabin, things like that. So this is information for passengers on airplane. And at some point there are missing information over here. So how can we deal with the missing information? One way is to extrapolate. Like you take these things here and extrapolate the missing information, or take the average between the previous, and then like you average the one before and one after, and then you add the value over here. So this is a small table, and then you can easily by eye identify the missing information. But if you have big data, like a million of data, it's very hard to identify what exactly the missing data is. And thanks to the Python module that's called pandas. So pandas actually has this function which is called isNull. So isNull immediately identify what are the missing information in your data. And also, not only this, but also Panda has this function which is called fill the NaN. NaN means NaN, like the missing value. And also here inside this bracket, you can fill the method or the methodology that you want to fill the missing information with. So everything is easy as far as you are good in Python. Well, so feature importance actually, as I said, in real world we deal with the data with the billions of inputs and things like that, and to analyze this data we need a very large computational power, like clusters of clouds of CPUs to analyze this data. And for that, to just reduce the cost, the power cost or the computational cost, then we do what's called feature selection. What that means? That means I choose, or I process or analyze only the most important features. And the other features which are not important, we can throw it away. So how can we identify the most important features? The point is the following. We could try actually a very simple model. Like for example here, we construct a deep learning multi-layer feed-forward neural network, right? So we have a bunch of input data over here, input features. And then I can construct a very simple one, a very fast one, like for example, stochastic gradient descent, or any simple one, or decision, very simple decision tree, for example. And then I try all the data, all the features. I give it all the features, and then I test the accuracy. And then I remove one after the other, and then I test the accuracy until I have this chart over here to see what is the most important one. And from there, of course, it's not computationally expensive, so I can throw away the unneeded data and the unneeded information. We don't need those ones. So we just keep focusing on the most important information that we need to analyze the input. Well, so the point number 2 now is how to handle the categorical and text data. Well, so assume that, as I said, this machine learning data actually it can contain text, numbers, clusters, and machine learning models deal only with numbers. So how can we do this change? Like for example, you have a column of color, and this column has three categories like the red, yellow, and green. So how can we convert these strings to numbers, right? So one way to use is to use what's called one-hot encoding. So one-hot encoding is that instead of having only one column, then we could have 3 columns. One for the red, one for the yellow, and one for the green. And as far as I have here, the row correspond to, for example, the red, then I labeled the red as 1, and the other 2 columns are zeros. Here, I have a yellow. Then the yellow takes 1, and the others are zeros, and so on and so forth, okay? So this is one way is in how to convert the text data into numbers. Also, in the labels itself, because at the end we need to compute the loss function. So if I have a multi-class classification problem, Like I want to classify the numbers of the digit m in this data set, where we have an image for numbers from 0 to 9, then we have a 10 classes, and I want to distinguish between them. So at the end, we want to compute the loss function. And loss function is y hat, the prediction, minus the true value all square of the modulus. So how can we do that actually, right? And the true value is either 1 or 0. So to do that, we need to do also one hot encoding. So if the image actually is 0, then it takes 1. If it's 1, it takes 1, and all the other zeros, and so on and so forth. Right? So for example, this is the label image of 5, then you find the 5 takes 1. If the image is this is 0, then 0 takes 1, and the rest is 0. And this technique is called one hot encoding. Okay. Well, good. So now we know how, or we just covered these two. Let's see what about the feature scaling. So feature scaling, it has been designed to solve the problem with the outliers. So the outliers is the data that are far away from the mean value or the median of your data. And the dangerous or the bad thing in the outliers is that it gives us wrong or false information about the trend of the data, the common feature of the data, how the data looks like. For example, if those are the true data that we have, those points are the true data, then we have some outliers, 2 points over here. So of course, those points they do not give us information about the feature of the data, right? Because they are extremely far away. They are false data. But if I keep the outlier in my model, then the model actually will focus on those outliers. Why? Any answer?
They are special.
No. Answer? Huh? Exactly. So they have a large weights. So the model focuses on them. So large weights mean when we compute the error function is large, and then the model will keep the focus on those to reduce the error function. And as you can see, as far as the model actually keep focus on those outliers, then it find or adjust the classification boundary such that the model actually learns information about the outlier, which is a wrong or false information. So if this outlier does not exist, then the model will exactly fit the true data. So that's hard. That's dangerous. So how can we identify the outliers? So we can identify the outliers by this box diagram. So what exactly the box diagram? So we have this box here, and this one here is exactly the center of the median. So this is this dash here, and then we have this bar, and those bar actually correspond to 2 sigma, 3 sigma in different way. So as far as you are more than 3 sigma away from the median, then you can consider this as an outlier. So now we know actually how to detect the outliers in your data. The question is, once we detect them, how can we deal with it? What can we do? So do you have any suggestion, Mike?
Somehow reduce it weight.
That's true. This is one answer. Another? Yes?
Take random samples from the lab.
No. Yes?
Very similar to scale them down.
He said that. Yes, he said that. Yes? That's true, but this is in case if they are small numbers. But if they are large and you throw them away, then you lost more information about most of your data. So, okay, good. So one way is actually to scale them, right? So we can scale them down. The second solution is that if the outliers in your data is a small number, then we can cut them and throw them away. The third one is that if they are actually large enough, then we can cut them and add them as a new feature, right? So here, how many features? It's 1, 2, 3, 4, 5.
And then for that one, we have lots of outliers. Then we can cut those outliers and add them as a new feature over here. So we can use them, like intelligent. Is it clear? Okay. Well, so how can we, this is the scaling, how can we scale this or how can we normalize this? So, for example, you can see here the x-axis for two distributions, x1 and x2, it ranges from 0 to 60. And there are some different values for the red and for the blue. So there are two ways to scale it down, or the scaling that we can use. The first one, which is called the standard scaling, and you normalize your distributions such that they obey or they follow the sigma z or the median z, or this is standard distribution, this one, the Gaussian distribution basically. The second one is that we could use what's called a min-max, and for the min-max you normalize the distribution such that the value is ranging between 0 and 1. And here there is a question. When exactly we can use this one, and in which cases we can use the second one? Yes? That's right. I'm sorry. Huh? Yes?
Depends on the weight.
Huh?
It depends on the weight of
No.
if I start scaling, if I want to return them close to the whatever the other points are, if I want to completely separate them, I would use
No. Don't look at this one. We are interested in the x-axis. So the x-axis now is from 0 and 1, right? But here it's from -4 to 4. No. The point is that if I'm interested, if the negative value in my data set is matter in this case, then I do standard scaling. If the negative value is not of much important, then I can do the min-max, because min-max is always between 0 and 1. So there is no negative value in this here. And most of the case, when we deal with image, we do a min-max scaling. Well, so this is like an illustration. It also shows you how the outliers actually hinders the classification performance or the accuracy of your model. So if we have two different weights like W1 and W2, and now assuming that W1 has a completely large weight or different scale than W2, then the model try actually, because at the end we sum, right? When we do this, when we minimize the loss function, we sum over all the weights, right? So if the model actually focus on one weight, which has a very large scale, then it might be most of the time W2, which has a smaller scale, is lost, right? So this is how the model looks like. It always focus on one weight, the largest weight, and ignore the others. So the main solution is that this is the case if we have two different scales between W1 and W2. So you see the model is unable actually to reach the global minimum. So that's important. But if we normalize them such that the two weights actually are nearly equal in the scale, then you can find that the model actually can easily converge to the global minimum of the loss function. So this is another illustration about the importance of the feature scaling. Well, so that's supposed to be yesterday after a very long lecture, but it comes here in the beginning of this lecture. Okay, and now this guy over here just got bored actually. And now he asked, can we train the deep learning model now? And the answer is no, not yet. Okay, so we have the full data. And this full data that we have in hand, we have to split it into 3 data sets. The first one is the training set, right? And this training set is the set we train the models on. And the test set, which is completely grabbed away data set that the model never seen before. And that's important. So we have to keep it in the same place. The model should not see it anymore. And there is what's called a validation set. So this validation set, like a subset, is a small set actually, and I use it to evaluate the training. But during the training, how do I know that the classification accuracy or the accuracy of the model reached, like for example, 90% or 80% or whatever it is? So we use this validation set to evaluate the training of the model. But this one has to be kept away and kept unseen. Otherwise, we miss everything. Well, so there is another problem about the size of the training of the data sets. So most of the time, if I wanted to do classification between two classes, maybe the data that I have in hand is not equal to the size of the data. Like for example, I want to classify between the blue and the red points over here, but as you can see, the blue points are very, very large than the red points, right? So if I train the model on this data set for one large data set and another small data set, do you imagine what's going on, what the model will learn? Okay, yes? Huh? Okay, so the model is going to learn more information about the blue points and less information about the red points, and that makes sense, right? Because the model actually doesn't have more data to learn from. It's only small data set for the red points, so it will learn everything about the blue points, but it learns a small information or low information about the red points. So how to rectify this? How can we deal with this problem? This problem actually called imbalance data sets, and in classification problem, this is very dangerous. So the first one is to reduce the majority class. Like we say, okay, I threw away more points here from the blue points, such that the size of the red points and the blue points are the same. But in this case, we lose information, right? So because I'm throwing away most of the points in the blue points class, and this is called undersampling. So we undersampling the majority class. The other thing is to do oversampling. Like we keep adding more random points, like I randomly captured, and then maybe we can add some noise, and then we add more and more points to the red. But here there is no major advantage, right? Because we repeat the existing points again and again, but randomly. The best solution actually, and which is very common to handle and to deal with this problem, which is the imbalanced data set, which is called smooth. And smooth is a synthetic minority oversampling technique. So this is how we abbreviate it. And the point is that smooth actually takes the minority, the points or the data of the minority class, and start to make lines between the data points, and then it start to random sampling or random generating points on these lines. So as you can see here, you see here how many points that has been generated, right? So this is the most efficient, common way of dealing with the undersampled data sets. Well, so now we can do the train of the deep learning model, and our first example is hello world in machine learning. And hello world in the machine learning is how to classify or how to construct a deep learning model to classify the handwritten image data sets. So what is this handwritten images? It's an image, the dimension of the image is 28 times 28 times 1. So those are like a grayscale images, and it contains the different categories from 0 to 9, and we want to construct a model that classifies between them. Like I give the model the image of 0, and then the model is able to predict this is 0, and so on. So how can we do that? Okay, so first let's look at the image. So as I said, everything in this wallet can be converted into numbers, right? So here, the dimension of the image is 28 times 28, right? So we have, how many pixels do we have? 784 pixels. And those are the small here. Those are the small pixels. And to identify the shape or the pattern of the image, then all unfilled pixels, we can give them a number of zeros. So you see here, this is 0, right? And the other bright pixels, we can weight them, we can give them a different scale. So if you look at the color scale, it ranges from 0 to 250. This is a very big scale, right? So we cannot deal with this. Then we have to do feature scale. So as I said, okay, so what kind of scaling algorithm that we can use here? Which method we can use? Standard scaling or min-max? Huh? No. Min-max. If it's not standard, then it's min-max, right? Because the standard, then you have this Gaussian distribution, and then you may have negative value. But in min-max, you normalize such that you don't have your pixel density is from 0 to 1. So here there is no any negative information enters or negative numbers entered here. So after we do that, then you find that now the scale is ranging from 0 to 1. So if you, is that clear? You see that one? The pixels. So okay, so this is 1 and all the rest are zeros. Well, so now we did the data preparation. Now our images are ready to be analyzed by machine learning model. So how can we do that? Okay, so we can take all the pixels. So the pixels now leaves in 2 dimension, x and y. Then we can flatten them. So we flatten them in one array. And this array now is, the dimension of this array is 784. And if you remember at the beginning of this lecture, how can we construct the first neuron from the inputs, right? So we have all the weights connected to the first neuron, and then we have W1, E1, where E1 is the input of the first neuron, W2, A2, which is now, this is the weight of the second neuron times the input of the second neuron, and so on, until we have W and AN plus the bias. But please do not forget the sigma, the nonlinear activation function. Okay? So this is very obvious, this is very known, and we have discussed this yesterday. So now we have constructed the first neuron, and now we need to initialize. Right? So we agreed that we initialize the weights randomly. After we do that, then we have everything ready. So we have constructed this guy here, then we can repeat the process more and more until we build the second layer, hidden layer, the third hidden layer, etc., etc. And this is like a model summary. So, and this is also a detailed summary from the TensorFlow and scikit-learn framework. So as you can see here, this is the flattened layer that I was talking about, and the dimension of this, the shape of this layer is 784. And now we have another this layer, this one. It's the dimension is 512, and so on until I have the output is 10, like a 10 neurons, and each neuron is a measure the probability of the measured image, or the predicted image, the predicted number. Well, so how can we now do the forward propagation? So now we have the model, the neural network model is ready. Then we give the image, flatten, pass everything forward, and then we do the predictions, right? The y hat, and we take this y hat to compute the loss function. That's normal, right? We discussed this many times before. And now the y hat here, I have a 10 neurons as an output neurons. So we have 0 means that the input image is most likely 0 image, contains a 0 number. 1 means that the input image are most likely image of 1. So as far as this one is a 3, then you find that this is the neuron that actually carry the most, the highest probability. And of course, the probability is ranging from 0 to 1, right? Well, so this is how it looks like. This is the labels that we have because this is supervised learning problem. So everything is zeros because this is one hot inputting, except the 3. It has 1. And those are the probabilities that been reported by the machine learning model or the neural network model. So as you can see, the model actually predicted the probability for the input image to be 0 as 43%, for it to be image 1 it's 28%. For the image to be image 3, which is the exact answer, and this is 88%, and etc. etc. So now we compute the predictions, and we have the target or the label. Then we can compute actually the loss function. We do the back propagation and the back propagation to update the weights, such that we minimize the loss function, and we start digging down, down, down until we get the global minimum of the loss function. So during the training, so if you remember what's called the e-box.
Number of iterations.
Exactly. Good. I'm happy. Okay, so this is the accuracy. And as you can see, as here we have almost 20 iterations, 20 e-box. So at the beginning, the accuracy was very, very low. And as far as we keep iterating, it means that we keep updating the weights. That means we are going into the direction of the global minimum of the loss function. We minimize the loss function. And then you see how the accuracy is just getting higher and higher. And on the other hand, it's exactly the same, but here I'm plotting the loss function. So for the beginning, at the random initialization, the loss function was very high. And as far as update the weights for to go to the minimum, the global minimum of the loss function, then you see how the loss function is minimized. Now the test. So after I finish training the deep neural network, then I test the model. So how can I test that one? It's simple. I give image from like random image, and then I said, okay, please predict the probability of this image. And as you can see here, this is a very nice results because we have almost 97.5% accuracy. That's very optimal. This is very good. So the prediction of the model here, I saw here, this is the predicted value, is also optimal. So there is no more misclassification in here. So for example, I give the image of 7, the model predicted value of this one is most probably it's a 7. Well, so that's all, but I just want to discuss a little bit more different things about the evaluation. How to evaluate the model. Basically, what the accuracy means. Does anybody know what is the accuracy mean? No. Okay. So these are the output of the model. Like if we have two class classification problem, then we want to distinguish between two classes. Then this is the output, whatever it is, like PDT, deep neural network, any other machine learning model, but this is like the output probability of the model. And then this probability, it has 4 different classes or different categories. The first one is the true negative. Like I have a negative and I have a positive class. The negative is, for example, the red points. The positive is the blue points, right? And this, the output actually is ranging from, for example, -1 to 1, and or from 0 to 1. If the negative is most likely clustered on the 1, then that's true. So I know this is a negative, and the model predicts this is a negative. Okay, so the model knows this is a red point. And also if it's a positive and it ranges more or going more to the probability of being 1, then this is what's called a true positive. So it is a blue point, and the model actually classified them as a blue point. The bad thing is this intersection area over here. And those are the false negative. So those are red points, but the model predicted them as a blue point. Here, the false positive, those are blue points, but the model classified them as blue points, as red points. Give an example. So we have a woman and a man. Both of them goes to the doctor. So the positive here is being a woman. The negative is being a man. And going to the doctor, and then the doctor predicted that this is our machine learning model. So the doctor here lays the rule of being a machine learning model, okay? And then the lady goes to the doctor, and the doctor says, okay, congratulations, you are pregnant. So a lady is pregnant. So this is a true. The lady is being pregnant, but also positive. She's a lady. That's clear? Okay. On the other hand, he has a man, and we classify the man as our negative hypothesis. So then the doctor, which is our machine learning model, is say, okay, you are a man, then you are not pregnant. So that is true, negative. Negative as a man, and the true that he cannot be pregnant. But if our machine learning model is messy, then he come to this guy and say, okay, congratulations, you are pregnant. And this is what's called false positive. Or see the lady, which is supposed to be pregnant, and say, okay, you are not pregnant, but she has symptoms that she is pregnant. And this is the false negative. And actually after that, I become skeptic about my future. So I asked ChatGPT. I said, okay, hey GPT, I am a doctor. Can AI take my job? Because I don't want to go to the doctor at some point and say, okay, well, congratulations, you are pregnant. I don't want to do that. So here, ChatGPT actually answers and said, okay, no, AI cannot take the job of being a doctor. So we are safe as men at this point, or even in the future. This will not happen. Okay, so another classification metric, which is called ROC. I don't want to discuss this. Okay, maybe you discuss that. Okay, so from the true positive and false negative, false positive and true negative, we can construct a matrix. And this matrix is called confusion matrix. So from here, we can define a bunch of metrics, like evaluation metrics. The first one is called the accuracy. And the accuracy is that true positive plus true negative over all the probabilities. And in this accuracy, it's deal with both positive and negative classes in an equal form. Okay, this word, I don't know. Precision is basically true positive over true positive plus false positive. So it keeps interest on the true positive class. Same as this one, it keeps interest on the negative class. But here there is also a recall. And this recall is the true positive over true positive plus false negative. So what is the difference between accuracy, precision, and recall? Accuracy, it quantifies the model ability to give you a true prediction on both classes, the positive class and negative class. Precision, it quantifies actually how good the model in predicting the specific category, right? So it quantifies or it evaluates the model ability to give you good predictions or true predictions. Recall, actually, it quantifies how good the model is at detecting a very specific class. So that's important to know the difference between precision and recall if you want to deal with some machine learning or data analysis problem. And now comes my question. Suppose you are a data scientist who is responsible for the data of passengers on airplane, right? So you have, for example, airplane that takes around 1,000 or maybe 500 people on this flight, and then the national security come to you and said, okay, hey, there is a terrorist on that airplane. Can you construct a machine learning model that predicts the terrorist, right? Just keep in mind, if you misclassify the terrorist, then the 500 passengers is gonna die. So that's important. You should not miss your classification in this case. And now the question is, how do you evaluate your model? Are you going to use the accuracy, or are you going to use the recall, or are you going to use the precision? Right? To identify who is the terrorist on the airplane. Just think about it. But this is really serious. Okay? Okay.
مش هنقول الحل؟
لا ده homework for you, just think of it. أيوة الحل مبدئيا الأول you have to think which is your positive and which is your negative, right? يعني مثلا أنت ممكن تقول إيه؟ خلاص أنا دلوقتي أنا عايز ألاقي هو إرهابي واحد في وسط 500 صح كده؟ I'm sorry, I'm just okay. So I have only one terrorist, and there are like 499 normal people, right? And the point is that what I am interested in to be precise when I construct the model. So am I interested to capture this terrorist or to design a machine learning model to classify or to be interested or identify the normal people? So this how you first put in your mind when you do this kind of things of search problems that what actually the machine learning model is designed for. So the machine learning model in this case is designed to learn the characteristic feature of the terrorist, right? So this is my positive. And now the question is, so if I miss classifying the terrorist, then there is a big probability that 500 people is gonna die. They are gonna die. So I have to assume that the 500 people on the airplane are terrorists, right? This means that I assign the positive class first. I want to identify the positive class, which is all people in the airplane are terrorists, because this is the safe solution. Like if I miss or if I misclassify a normal guy as a terrorist, then it's not a problem, right? هيروح شوية البتاع وهيرجع تاني. But if I miss the true terrorist, then this is disaster. And also, we should not actually, when we evaluate the model, we should not evaluate the model on the accuracy, because accuracy try an equal footing, right? It shows you or give you prediction on how the model actually is able to classify both of them. We don't need that. We need to consider the recall, where the recall actually is very precise. Evaluate the model, how the model is able to predict the true value in that people or that guy is a terrorist. So that's okay. So we have to finish at 4 sharp. So I'm going to discuss a bit here about the convolutional neural network, convolutional based neural network. And now the first question is, why do we need convolutional neural network models? DNN, or the fully connected deep neural network, can in principle analyze images, right? And we saw that in the previous slides. So why do we need convolutional neural network? Well, so when you do test the image, if you give the this image to the neural network, then the neural network, this is the probability. So as you can see here, this is the probability of classifying the input as a 0 image. 1, 2, 3, 4, 5, 6, 7. So the model actually predicts or give a probability of 1. This is a 7 or an image that contains a number of 7. So the model is sure 100% this is an image of 7. But now think of this. We just flip. We rotate. So if you rotate the image this way, the model now changes its probability. So now it gives the highest probability to the model of being a number 6 here. And it assigns 1 times 10 to minus 7 probability of being a 7. So the fully connected deep neural network is not invariant under rotating the image. So it trains to identify a global information about the image, but not the local. And this is what we're going to talk about. So the fully connected model, which has the sum of all the weights to one neuron, it learns all the correlations between the pixels to each other. Like, for example, how to clarify the spreads. So if this is your image here, and then you have these pixels, right? And then you have some shape like 7, like this. So the model is fully connected. That means that it learned all information about these pixels and the correlation between those pixels together. So the model actually in this case learned a global feature of the 7. So as far as you give it 7, then it's stored and the model when you train it that this image should contain this shape, and this shape is identified with what? All pixels are zeros except those are ones, right? And now if you flip this like this, then you have a new features and new characteristic features for the image of being 7, which confuses the model. So now the question is, actually this kind of information is called the global information about the image or about the object. And now the question is, can we construct or can we find a deep learning model that can learn both global and local information about the image? So what exactly the difference between the global and local information? This is the original image. This is what's called the global information of the image, that the model understands the whole object, the correlation of the pixels or among the pixels that constructed the whole object. And this is the local information. The model actually learns information at different pixels independently. So the model stores information about these pixels apart from these pixels, apart from this pixel, apart from this pixel. So it learns information, local information of the image. So now our task is we need actually to cook a deep learning model that can learn actually both global and local information about the image. And that this one, how can we do that? Like first, how can we construct or how can we capture the local information? Like the local features that are stored in each pixel. How can we do that? We can do that by the concept of filters. So we can construct a filter which is now is a matrix like this, and then this matrix actually scan the image. Like this filter moves here. It keeps moving in here for all the images, like scan a whole image, and the captured information can be mapped in a different layer or a second layer, and this is called a feature map. So the image actually, or this filter scan the image trying to look for a very specific feature of the image, like for example the nose of the dog, the eye of the dog, the tail of the dog, the legs of the dog. So I can actually have lots of these features or these filters that can scan the image such that each one of those filters actually can learn a very specific local information about the object inside the image. Like for example, the first one here can learn information about this, the nose of the image, right? The ear of the image. This one here can learn some information about the leg of the dog, and so on. So this is how we construct that. Let me show you one thing that we have here. Yes, good. So this is how it looks like. Here we have a filter, and then this is an image of a guy. Okay, so this is a human face. And then we have a filter, and that filter is designed to capture the feature of the eye. So as you can see, the filter actually scans the whole image, and it gives everything. This is I know, it's 0, I know 0, I know 0, right? All the pixels, and then find the eyes here, right? So this filter actually can have more information about local structure or local feature of the image of this object inside the image, which is the eye. And actually, if you look now, look, this matrix looks like the 2 eyes, right? So you have 2 eyes here and everything is zeros. So this is how these filters actually can capture local or learn local information about the object inside the image. Well, so to construct now a machine learning model that learn both the local and global information, then we need this structure. Only this structure and nothing else. So as we said, the convolution layers, which are filters that scan the image, this one capture the local information, right? And then you flatten all the information that you've captured, and you add a fully connected linear network. This is the one that we studied before, right? Yes?
Is the local features we specified?
No.
The model specifies.
That's really good questions. That's really good question. You design actually a matrix, your filter. You said, okay, my filter is 2 times 2, right? So this is your scanning filter. And now you just initialize the numbers, the weight here in random. And then you keep scanning the image, and at the end you measure a loss function, you minimize the loss function such that this guy capture a very specific good local information.
So we only identify the number of filters.
Exactly.
We need to identify the number.
Exactly. Yes. Sorry? You can have lots of filters. That's it, right? So it's not only one filter. Yes. So actually you decide the number of filters here. How many filters do we have? And then these filters actually scan the image with some numbers. And then at the end you measure as far as you minimize the loss function, you will find automatically these filters actually capture yes, this is kind of data interpretation. But this is depends on the problem that you want to solve. Like for example, I'm going to give you an example on how to identify here. Okay. Yes, like here. This is like a given example. This is a task, like given a bunch of image, like human images, and we want to classify either the this face or the human face actually is smiling or not. So in this case, we have to focus only on the face of the human, because we have to measure the features of being smiling or not. Like here. This can be there's a advanced, very advanced conclusion of neural network don't need to process the parts of the image that you are not interested in, like backgrounds. Or there's also what's called regional sequence. Regional sequence. This also is designed to just throw away you're not interested in the background and focus on the objects. But those are very, very advanced techniques. And if you learn some of them, you just guarantee your position in some of the high-level machine learning companies. Okay, well, so now the question is, the structure of the convolutional neural network should be consists of two parts. The first one is the convolutional layer, and the second one is the fully connected layer. So we know now this convolutional layer could capture the local information of the image, like very specific information, edges, for example, eyes, nose, mouth, whatever. But also we have to add the fully connected layers. So do you have any answer why we should have the fully connected layers?
Is a regular deep learning
No. That's true, yes. So as you see here, if we know like edges or specific or local information about the object, at the end we don't know, right? Because those here, those filters, they do not talk to each other. So if I got a completely separate information about some mouth, eyes, nose, hair, how do I know what is this object is, right? So I need to have a full picture, like a global information about what is this object actually is. So first we have this convolutional neural network to capture all the local information. Then we need the fully connected layers to gather all the information and make a very big picture, very big picture about what are those captured local information is about. So this is how we do it, right? So we need both. Okay, so maybe we can postpone this to Wednesday. Okay, you agree, right? I feel you're, I see you're all exhausted. So we can talk about this like on Wednesday. And Wednesday I'm going to give 2 lectures. We are going to continue dealing with this one, explaining how these things work in detail, how this the filter is actually able to capture local information, and also I gave you some good intuition about the color scales, like the color image. How can you analyze also color image, not every image? Okay, so anyway, see you on Wednesday. Any questions?
I think my question is really general, but I don't know if it's good to ask it now or the end of, or at the end of all the lectures. But there was a statement that I saw in some course that when using machine learning, especially in complex data, deep machine learning, they are like black boxes. If we don't to make as a physicist, when I use machine learning, I want to learn a new physics.
Yes.
But the machine learning in itself is like a black box.
No, it's not. Who told you this?
It was a statement in the course.
It's a wrong statement given by the tutor of the course.
Oh, maybe I misunderstood. What
Because here I show you how can you open the black box. So this is what's called CKA similarity, or central kernel approximation theorem, and how can you open up this black box and learn what's going on inside the hidden layers. So it's no longer black box. There are lots of techniques nowadays. It's called explanatory machine learning models. Try to explain what's going on inside the black box, or what people call it black box.
So I can use the machine learning to learn new things.
You can construct a machine learning or a different method such that you understand what the hidden layers actually captures information.
Because as image processing, we human do it like easy. But like if we look like a
No,
data,
not easy.
we can human can like smiling faces.
If you can do that, why do we need a machine learning?
No, we need it because we don't. If we have a very large set of data, it will be a problem for a human. But
Yes.
in specific cases.
And also there are some complicated image you cannot distinguish by eyes.
I know, but my point is like data from like about climate or about the physical process. We human learn how to define the we learn like in college how to specify the differences or the special
Features.
features in it. But if we can use machine learning to find this special feature, then this will like be a shortcut. That is my point. So we need to know. I think I'm not sure. We need to know how the machine learning have done it, so we can have like a new physics.
No, we don't. We cannot understand or know how the machine learning process this. So because it's billions of numbers just are running over here, but we could have a general intuition about the captured information or what like each hidden layer actually captured. Like what is the information that being captured by each and every hidden layers in your model. But of course you cannot process what's going on because there are like a millions of billions of numbers, and at the end you will do nothing with those numbers. But you could have like a general intuition what's going on. And this is what we are going to discuss here about the central kernel approximation theorem. Yeah, any other question? Okay, so if not, then see you on Wednesday.